Welcome to this talk on planetary population synthesis, comparing theory and observation. This is Chris Mordasini speaking. I'm working at the University of Bern in Switzerland. This talk consists of two parts. First part is an introduction and the methods, and the second part on the results and the perspectives. And in part one, I'm going to first give you an observation motivation for population synthesis. Then I'm going to talk about the principles, then the input physics, the initial conditions, and then the observational biases. So let me start. This observational diagram. Motivation is a diagram that you, of course, know very well. So here we have the mass distance diagram, and now we look at it as a function of time. And this is us back in 1994 with the solar system planets. This year is obviously 51 Peg B, discovered in 1995. And since then, you can see this enormous increase in observational data on exoplanets, which comes data and detections both from the ground and from space, from all these different missions, and also many more that I have indicated here. And in the future, even much more is good to come pretty soon, and we're going to hear about that at the very end again of this talk. Looking quickly again at this mass distance diagram, or also the distance radius diagram, what you see is that there is a huge diversity in exoplanet properties. And what we would, of course, like to do is to use all these observations to better understand how planets form and evolve. However, what we have to say from a theoretical point of view is that the field remains observationally driven. So typically discoveries are made and then theoreticians try to explain them. So theory struggles a bit to keep up with this very fast progress. And we can wonder a little bit why. And one reason for that maybe becomes obvious when looking at these two images here. One is a micrometer size dust grain, very early stages of planet formation. And then below we have Jupiter's south pole, so a huge object. So planet formation, we can say, certainly is a complex process. And one of those is illustrated by these two pictures here. So we have to deal with a huge range in spatial scales, from dust grains to giant planets, and each scale has its own challenges, its own specialities, its own physics. It's also a pretty long time scale that we have to consider. It takes millions of years, even billions, if you wish, until to go from the grains until we have a dynamically stable, fully fledged planetary system. Then we have a lot of different input physics. Of course, we have gravity, but also hydrodynamics, thermodynamics, radiative transport, magnetic fields, high pressure physics, impact physics, and all of that. And we have strong nonlinear mechanism and feedbacks. An example is orbital migration. So there, the gas disk makes the planet migrate, but on the other hand, the planet also feeds back onto the disks and can cause the formation of a gap. And this then in turn influences the migration rate. So we have to consider this process together in a self-consistently linked way. Now, physicists would usually go to the lab to make some experiments, but okay, it's a little bit difficult to have in a lab experiment a giant impact or something like that. It's only for special regimes like dust grow or something like that. Otherwise, you cannot do that. And also the numerical approach is not possible. It's not possible to have really a complete long time 3D radiation magnetohydrodynamic simulation of the whole process as a high resolution. Would take forever to do that. And this implies that we cannot really build theory based on the first principles of physics only. Instead, what we need is that theory, that it gets some observation guidance. And this, of course, happens via the comparison of observations and theoretical predictions. In practice, this is, however, not so easy. And the reason for that is the following. First, when we set up a theoretical model, typically we do that for one specific process, like orbital migration, like the dust of the drift of dust, like the accretion of pebbles, like the accretion of gas, like n-body interaction, and all of that. But what we see, of course, when you observe the solar system or the exoplanets, it's not, we cannot see the imprint of only one specific process, but what we see is the result of the non-linearly combined action of all the mechanisms that are acting during planet formation. And this can be difficult to say what effect causes what. Then second, for exoplanets, we only have pretty limited knowledge typically about an individual exoplanet systems, like a period and the radius or a minimum mass. There are, of course, some exceptions where we have much better knowledge, but this is only a relatively limited number of systems. For the large majority, we don't have that. But what we do have, of course, and this is illustrated by this AM or period mass diagram, is that we have now a very high number of exoplanets, and they, of course, can be treated as a population, and as such, they give statistical constraints with which we can compare our models to. And ideally, here we can give nowadays also have data from different techniques. So we get constraints, not only as in the beginning, maybe from minimum mass and period, from radial velocity. We also have radii, we have magnitudes, we have atmospheric compositions, we have spectroscopy, and all of that. So we have many different constraints that ideally we put together. But what we now need is a tool to use this wealth of constraints. And this is where population synthesis comes in. So population synthesis is a tool to use all the known exoplanets to constrain planet formation and evolution theory. It's a way to observationally test the implication of theoretical concepts. So maybe you find that it is in disagreement, and then you have to move on with a certain theory. It can also be used to predict the yield of future instruments. This is interesting, the observational side, and as such, it totally provides, I think, a good link between theory and observations. It is a statistical approach rather than comparing to individual systems, although this is another aspect which is equally important, comparing to the solar system or to some special systems like TRAPPIST-1 is of course also important. So here in this statistical approach, what we need to do is of course to compute the formation of many planetary systems, and this implies that the approach and the physics must be simplified. Typically they are low dimensional, and we will come back to that later to know what this means. But it of course must capture the key effect. And what it does is it is to try to build on the detailed studies of specific physical mechanisms, to combine them all into a global end-to-end model, and then to compare that with observations. And with end-to-end, what I mean here, this is a model which directly starts with disk properties and then gives as output observable properties of the full planetary systems that is predicted to form. So it includes all the process from the beginning to the end. And because it builds on these detailed studies, it reflects also the general progress of the field. Now, a few words on assistion statistical constraints. We hear about that in other talks, but let me maybe still tell you some of the most important ones. Certainly, this is the mass distance or mass period diagram, the minimum mass here. This is from a recent radial velocity survey with Carmenes. Then this is we saw this plot. This is a semi-major axis versus mass from direct imaging. In principle, the y-axis is rather magnitude. So here it's already converted into mass. Then another very important one recently is this. This is period versus radius or planet size. This is, of course, from the Kepler survey. And then we can have the one-dimensional equivalence. This is from this distributions, 2D distributions, it's mass distribution. This was again from radial velocity. This is a mass distribution from microlensing. This is the radius distribution with the Fulton gap that we also hear about. And then another class of important constraints are dependencies of planetary properties on stellar properties. So this is the metallicity, for example, here the well-known increase of the fraction of stars with giant planets as a function of host star metallicity, or another one here is the frequency as a function of stellar mass. And there are more things we could study, like the impact of the cluster there are other quantities like the eccentricities we can study, and then also combine things like the mass-radius relation, which tells us something about the bulk composition, for example, the content of heavy elements, and then also all kinds of constraints that come from the architecture of multi-planet systems, like the multiplicity, the piece in the pod effect, or the relation between close-in super-Earths and outer cold Jupiters. And all of that comes in, and in the best case, we combine here all these constraints from all the major detection techniques, and not to forget also that the solar system is, of course, still the most important benchmark system for any formation model. So we should also study this one. And then what we see is that formation theory can certainly not explain all these observations nowadays in one coherent picture. We are not at all there. But I think at least for some, it can give us some clues about possible mechanisms that might cause some observed property. Good. Let us now move to the population synthesis principle. And as we will see, one of the most important ingredients of that method is these end-to-end or global models. And for that, we should quickly have a look at what are all the different physical effects that come into play when a planetary system forms. And for that, we can have a look at maybe what we can call a sequential planet formation paradigm, which combines a little bit all the different understanding that we have achieved from studying the solar system and the extrasolar planets. And of course, everything starts at the moment where a young star, a newborn star forms, at t equals 0. Here you have a number of protoplanetary disks. So we first have a protostellar disk and then planet-forming disks. And in those, we start the process in the class 1 and class 2 disks when the gas disk is present. And we start at the very beginning with this micrometer-sized dust, and this dust can grow relatively quickly to pebbles, which are then centimeter size. It depends where you are. And the very important effect during that time is the inward drift and the coagulation of this dust and pebbles. Then the next step is the formation of planetesimals, probably via the streaming instability, and these planetesimals can then continue to grow to protoplanets now via collisions, and gravity is now the most important force that is acting. Over the time scale of a few million years, maximum 10 million years during the protoplanetary gas disk lifetime, some of these protoplanets grow massive enough, about 10 Earth masses, to become able to attract large amounts of nebular gas, and therefore this is the formation of a giant planet. And this bottom-up process here, this is called the core accretion theory. The process that is important in these steps here is orbital migration, so the radial movement of the protoplanets through the gas disk to the exchange of angular momentum. Most of the protoplanets don't become massive enough to become a giant planet. Rather, what happens here is once the gas disk has dissipated, and therefore also the damping effect of the gas, there the orbits destabilize, and we have a series of giant impacts, and this leads to the formation of terrestrial planets on a timescale of about 10 to the 8 years. And something which goes on basically until the end of the main sequence is a dynamical evolution. So the planets, they interact gravitationally and settle into a configuration which is stable over billions of years. During the same time as we have this dynamical evolution, we also have a thermodynamic and composition evolution of the individual planets. Like giant planets, they cool and contract. Close-in planets, they lose their envelope, their atmosphere through atmospheric escape. And terrestrial planets, for example, they undergo all kinds of geophysical effects like core formation, continental drift, and outgassing of secondary atmospheres. Now, even at this very simple sketch level, there are uncertainties. For example, it's not so clear whether planetesimals are really the most important building blocks for protoplanets, or whether protoplanets mainly grow directly by the accretion of pebbles. Maybe this is also a function of orbital distance. And there is, of course, a completely different idea about the formation of giant planets. This is the gravitational instability theory. So there, a large patch of the protoplanetary disk, gas disk, becomes unstable to its own gravity and then forms a giant planet very, very quickly. Now, this is a short overview, but I think it already tells you that global end-to-end models, they should, in principle at least, include all these effects. And this is quite a formidable task. And therefore, we have to do something that it's still a task we can actually achieve. And this is shown here. So how we try to get the essence here of this population synthesis idea. So we need the specialized models, theoretical models for migration, accretion, and so on, to know what is important. What we then try to do is a kind of an extraction process. So we try to get the essence from these models, but of course we lose the subtleties of the original. But still, what we are left with is a concentrate of many effects, and hopefully, because it can directly predict observations, it allows you to see the big picture. The challenge here is, of course, is to know how strongly one should distill. And this is shown here at the example of a protoplanetary disk. So do we need to simulate it in 3D in a magneto-hydrodynamical simulation, maybe even with radiation? Is it necessary? Or can we simplify it into a one-dimensional viscous evolution equation where we just study the evolution of sigma? Sigma is the gas surface density as a function of time and orbital distance. Or can we simplify it even more and just write down such a parameterized law, power law dependency with some exponential decrease? This is, of course, always a big question, and it's not always so clear. In any case, let's assume that we have such a model, and let's see how this combines to form the whole approach. So, as I said, we start with the models of the individual processes, and we try to use them to create a global end-to-end formation and evolution model, which can directly predict planetary system properties based on disk properties. This is the most important ingredient. The second most important are the initial conditions. So we then want to run these global models not always for the same initial conditions, but for a choice of different initial conditions. And these initial conditions, these are the properties of protoplanetary disks, and they should reflect how likely a certain disk properties is also in reality. And we'll come back to that later on. So here we have again some of these examples. So we have now this probability distribution of these initial conditions. Then in the next step, we draw from them. And each time we then use our global end-to-end model to produce one synthetic planetary system. And then we do that many, many times, which is actually can be quite time consuming. We'll come to back to that also. In the next step, and like that, sorry, like this, in this step, we then get the full underlying synthetic population. However, for the comparison, we cannot compare just this full synthetic population because obviously, observationally, in reality, we cannot detect all planets. So what we need to apply in the next step is a synthetic observational detection bias. And like that, we then get the subpopulation of detectable synthetic planets. And this one, we can then now compare with the actually observed population. We do all kinds of statistical comparison, like the frequencies, the occurrence rates, the orbits, the radii, luminosities, the architectures, the correlations with initial conditions and with stellar conditions, and so on. And in most cases, we will find that there is no match, or at least no good match. And what we can then go is go back to our initial models, change parameters, improve the models, reject the models. And like that, we get this feedback loop that helps us to understand a little bit better how planets form and evolve. Sometimes we find some model which matches at least in some aspects. And then we have an interesting situation because we can then use this model to make some predictions. So going back to the full synthetic population, and we can make a prediction what happens if the inner working angle of my direct imaging instrument of the next generation is only, I don't know, half as large as it was for the previous generation. And like that, we can then build new instrumentation, which gives better observation constraints informed by what would be most helpful for theory. And this gives us then a second loop. And one thing that is important to understand is that one learns a lot, even if a synthetic population does not match the observed one. This is not by itself a problem. This is actually the point, because like that we can see which models need to be improved further. Good. Let's move to the next part, which are the global models and the input physics that they use. So we are here at this step now. I will now, for the rest of my talk, I will go through all these different boxes and always discuss them in a little bit more detail. And I looked a little bit what is maybe the earliest, or at least the earliest population synthesis I know. This is this paper here from the 1970 from Stephen H. Dole from the RAND Corporation, and the title was The Computer Simulation of the Formation of Planetary Systems. And he actually did something which in many aspects is still what we still do nowadays, only that the input physics has changed. So he says that he tests the hypothesis of the nebular formation of the solar system. So this was obviously for the solar system. And he does that with a computerized Monte Carlo simulations. And he does that by injecting, as he says, nuclei, so small protoplanetary embryos, and looks how they grow. And this is based on the nebular hypothesis and some kind of early core accretion paradigm, in the sense that there's first an accretion of the solid cores and then the accretion of gas if the core is sufficiently massive. So let's look a little bit more at this input physics. So the disk model was static in time, is an exponential profile. The accretion of solids is approach limited or derived from the restricted three-body problem, and he already had the concept of feeding zones. He also had some kind of critical mass, although how it's derived was more or less dependent on this parameter here, k crit, which was a free parameter. He had a more or less arbitrary parameterization of the termination of gas accretion. He assumed that embryos coalesce once their feeding zones overlap, and the orbits were fixed. So this was in situ formation, no migration, and also no n-body interaction, except that they coalesced once their feeding zones overlap. And the most important parameters were the stellar mass, the disk profile, the seed mass, this k crit for the critical core mass, and also the maximum masses. And the Monte Carlo variables were the position and eccentricities of the initial seeds, the disk mass, the disk dust to gas ratio. And this is what he then found. So here you see 5 different realizations, always same model, but different initial positions. And you can see that he could get something, and this was a little bit inherent in his setup, which looked, of course, like the solar system is close in small planets and giant planets, and then outside again, smaller planets. Something like solar-like systems with a uniform spacing in log, and this tuning to this solar system-like architecture. So we had no close-in super Earths or super-Neptunian planets, and he also had no distant giant planets. But he, in his model, regarding the physics, there was something like isolation mass for planetesimal accretion and the critical mass for gas accretion. But the problem that he faced, that at that time, his paper predated much of the specialized models for important fundamental individual processes on which we rely nowadays. And this is, it was pre-viscous accretion disk theory, it was pre-planetesimal accretion theory, it was pre-one-dimensional planetary structure theory, and he also predated orbital migration theory. And this illustrates the reliance of global models on the models for specific processes, and of course on observations. And you could say that maybe if we now look at this, what he assumed, we would say, okay, this was not very helpful, these assumptions about the specific models. Maybe in 50 years, they're also going to say that the specific models on which we build our global models nowadays are maybe also not all the end of wisdom, but this is, of course, this progress, which is typical for science in general, I would say. So now let's move forward. 2004, Ida and Lin presented the first modern population synthesis model. So here the disk model was still a power law with an exponential decrease, but now the accretion of solids was of planetesimals via the Savaronov rate equation with an isolation mass. The accretion of gas now was derived from parameterized Kernel-Helms contraction, and a fit to critical core masses obtained from Ikoma et al. The termination of gas accretion was now based on physical process like gap formation or global disk dissipation, and the embryos were treated the following way. So at the beginning, they assumed only one embryo per disk. This was a typical approach in initial population synthesis models and still being used in some models. And later on, they switched then to a semi-analytical prescription for the n-body interaction. So it's based on fits to orbital crossing timescales, and they included type 1 and type 2 migration. And the Monte Carlo variables were still similar: the positions of the embryo, the disk mass, the dust to gas ratio, and the disk lifetime. And later on, they added several improvements like dead zones in local enhancements of the solids or new type 2 migration descriptions. And this is what they find. So this is a typical output of a population synthesis model. So you have here 4 different models showing the predicted mass distance diagram. And what they could, of course, now show is that they could now reproduce the observed diversity of the extrasolar planets. It was the big new progress, I would say. They also had the prediction of a planetary desert. So the absence here of intermediate masses, because here we grow quickly in gas runaway accretion, or rather in this part here, which might or might not exist in reality. We come back to that later. They also looked at what are the consequences. This is here, these different models of different termination laws for gas accretion, and they also studied the effects of orbital migration. Nowadays, there is quite a number of population syntheses are on the market, and I'm only not giving you all of them, but some of them. So the Ida and Lin models we just heard about, core accretion is planetesimals. So this is a very fast, customized model for population synthesis. And as I said, it first had the one embryo per disk approximation, and then the statistical n-body for the interaction. By the way, if you're interested in that, there is a similar open source model available at this address here. Then the model I'm going to talk about more in the rest of the talk. This is the Bern model. This is also core accretion with planetesimals. This is a combined formation and long-term evolution model. And compared to other models, it tries to solve the underlying differential equations more explicitly, like the n-body integration is explicit, or also the internal structure model, or also the disk model. Going back to that later on. Another important model is the Lund model. Here, this is core accretion, but with pebbles. They have a single embryo per disk, but they have 2D disk models, which are derived from radiation hydrodynamic simulations. Then there is also the McMaster model, which is core accretion as planetesimals. Each emphasizes the role of traps in the disks, includes astrochemistry and also internal structure, and also the long-term evolution. On the gravitational instability side, there are also several population synthesis methods by these authors here, and they include criteria for fragmentation, for the clump contraction, for tidal downsizing, for migration, and also sometimes for the accretion of solids into this clumps. So there is quite a lot of models nowadays here. Let me focus on the Bern generation 3 formation and evolution model. It's based on the core accretion paradigm, and this plot here, this confusiogram, shows you all the different sub-models which are acting at different moments in time. So first we have some which are acting during the entire time that is studied, so during formation and evolution phase, so from 0 to 10 gigayears, and these are things like the internal structure of the gas and the core, then bloating and deuterium burning, and an atmospheric structure model. Then we have some modules which are active only while the gas disk is around. So for the radial structure and the vertical structure of the gas disk. Then we have some more models which are active during what we call the formation phase, which is set to 20 million years, but 100 million years would probably be more realistic. So this is the planetesimal disk, where we have planetesimal accretion and where we have the n-body interaction. And what we then do during the evolution phase, so from 20 million years to 10 gigayears, we then evolve each planet individually. So here in the formation phase, they can interact gravitationally, they can scatter, they can collide. But here, then we assume that each planet, the orbit is fixed, and they only evolve through the effects like tidal migration is the star, and the mass can still change via atmospheric escape. The emphasis of this generation here was on the direct prediction of all important observable quantities. So not only masses and orbital distances as in the past, but directly also radii and magnitudes, luminosities, and also the ability to simulate planets ranging in mass from Mars to super Jupiters, and also from very close in distances to large distances. And this means, for example, that the model needs to include the giant impact formation phase for terrestrial mass planets, but it also needs to include things like atmospheric escape or bloating of the radii in order to be able to simulate close-in planets. And here you have a lot of references on which all these different papers that these different modules, which individually can actually quite complex, rely on. And some more illustrations. So here first the disk. So we have a star which changing properties. Here we have our disk, which is resolved radially and integrated vertically. There we have processes to get the temperature, like stellar irradiation, viscous heating. This gives us then the mid-plane temperature. Further out, the disk can be destroyed or can lose mass via photoevaporation, and it's a viscous accretion disk, so it accretes onto the star. We also have planetesimals inside. They have a certain dynamic state, but they are not individual particles, but represented by a surface density. And there is also actually a chemical model which gives you something about the composition, like icy and rocky bodies. And we then embed into this disk planetary embryos with a small initial mass. Then what about accretion? So here the planets, they have a feeding zone from which they accrete planetesimals with a certain probability, collision probability, and they also have a gas enhanced capture radius. Then the gas accretion is given by solving the one-dimensional internal structure equation. So this gives how quickly the envelope cools and contracts, and then can therefore then accrete new gas. This depends a lot on the opacity in the gas envelope, but also leads the luminosity and the radius. And there are different phases. There is the so-called attached phase. Then it detaches. This is when the radius contracts quickly and when also a circumplanetary disk can form. And then we have all kinds of interactions. So we have the gravitational interaction between the bodies themselves, between the planets. We have collisions, and we have orbital migration, and of course also the damping of the orbits through the interaction with the disk and the orbital migration. And more effects that are included are, as I mentioned, bloating, diffusion, atmospheric escape, and some other things. So this, I would argue, is quite rich in physics, but it's low dimensional in the sense that planets are assumed to be spherically symmetric, while the disk is assumed to be rotationally symmetric. So it's 1 plus 1D radial and vertical directions. And there are situations where this is a good approximation, but there are others where it is not such a good approximation. And the reason for that is that in these low dimensional models, we can follow the formation and evolution of the planetary system over the full time scale. If you have a 2 or 3D hydrodynamic simulation, you can typically follow the system only for tens or maybe hundreds of orbits or so, not more. You should also mention that there are still many effects that are neglected, like the early phases for the solids, the growth from dust, to pebbles, to planetesimals, to protoplanets and pebble accretion, or new insights into protoplanetary disk structure like the disk rings. But already now, the numerical simulation of one planetary system in this model here, starting from 100 lunar mass embryos, takes about 3 months, which is mostly spent in the N-body and the planetary internal structure. And for this specific model, this means that this long calculation makes a parameter optimization difficult, but there are other faster models where this has been done, like for example in a paper of Chambers a few years ago. So let's move forward to the next aspect of the population synthesis models. And these are the initial conditions. So we are now here. So of course, what is the underlying assumption of this population or of this approach is the following is of course to say on the planet forming disks, there is a very large observed diversity too, not only on the planet side, and things of course, thanks to the ALMA revolution, we know a lot of constraints now on these disks. And so we can try to observationally determine the distribution of the disk lifetimes. And here the stellar cluster environment is important, the disk gas masses, the disk dust masses, and the sizes. And we then wonder if this diversity of disks, so the diversity of the initial conditions, is the cause for the diversity of the planetary system as the end products. And we wonder if we can statistically reproduce that with a population synthesis model. And these Monte Carlo initial conditions are still similar. So let us now continue with the next aspect in the approach, which are the initial conditions. And so we are now here in this box here. So the underlying idea is of course the following, that what we see is basically the imprint of disk properties, because on the observational side, we now know of course that planet forming disks, they also exhibit a large diversity in all kinds of their properties like mass or size or lifetime. And what we can do, and what we have especially recently done thanks to ALMA, is to determine observationally distributions of essential properties of the disks, like the lifetimes, which depends on the stellar cluster environment, for example, the disk gas masses, the dust masses, and the sizes. And the idea is, of course, that this diversity of initial disk properties as initial conditions is the cause for the diversity of the planets. And it's always the same formation model, which might or might not be the case. So maybe it could also be a combination of core accretion versus gravitational instability. But this is another question. But this is now the hypothesis. And then we wonder if we can statistically reproduce that with a population synthesis model. And the initial conditions that the population synthesis models are using are typically the same as we saw already in these very initial old models. So the first is the metallicity, the dust to gas ratio, and often it is assumed that this metallicity is the same in the star and the disk, and then we can use the spectroscopically determined metallicities of stars. Like here you see the distribution of observed metallicities, and we can then convert that into a dust to gas ratio. And this is then just a fit to such an observed distribution. This is probably the distribution which is most straightforward to determine. The second one is already much more complicated. This is the initial disk gas masses. And here, for example, can one use results from such a ALMA and VLA survey of class 1 disks, where you see the mass distribution of this gas or of these disks. The next one, then the third, is the disk lifetime. Here we can use observations of the infrared excess, which tells us as a function of time what fractions of stars in different star-forming regions still have such an excess. This is from the original Heisch-Lada plot of 2001. We see that they decrease on a time scale of maybe here 6 million years. These are some more recent observations, and this is then here a comparison of these observations is a disk lifetime distribution of synthetic disks. And one way of doing that is to fix the alpha viscosity parameter and then to adjust the external photoevaporation rates such that the synthetic disks have a lifetime distribution that agrees with the observed lifetime distribution. And the fourth initial condition can, for example, also be the inner edge of the disk, which can be set to the co-rotation radius, which can then be derived from observed rotation periods in young star-forming regions. We will see later on that the most important initial conditions is actually the initial solid mass. So how many solids do we have in the disk, which is the product of gas mass times the dust to gas ratio. And here we see such a distribution. So we have disks, some disks have very low initial content, about 10 Earth masses, and the most massive ones have 1,000. And if we try to estimate how much solids we have in the solar system nowadays, so how many solids do we have in Jupiter and Saturn, in Uranus, Neptune, how many in the terrestrial planets, then we maybe get something here. So this is about in the middle maybe. And it's very important to stress that it's actually not at all trivial to derive certainly this observation, but also the radius of the disk, which I have not mentioned here, because it's not trivial to convert from observations to the theoretical initial conditions. Good, let's come to the last part here of this kind of the methods part, and this is the observational detection bias. So with that, as I said, we get the subpopulation of observable synthetic planets, and what we need for that is basically a result from a survey that you can see here. So this was from the original survey with the LOT instrument. This is a radial velocity, Bose's radial velocity. This was the instrument with which 51 PEG-B was discovered. And here you can see, as a function of semi-major axis and for different planet masses, all giant planet masses, how likely we could detect a planet, of course. And at 10 meters per second, of course, you can only detect quite massive planets. When you go very close, then you can also get some lower mass planets. But of course, when you then have a radial velocity instrument like HARPS, is 1 meter per second, then you can do a similar plot. Now we have period versus mass, and now the lines are the detection probability. And what we can see is, of course, close-in and massive is very easy, to detect with a probability of 100%, but detecting something distant and of low mass is very difficult. Like here, this is the 2% line. And these lines, they were derived taking into account the effects of orbital eccentricity, stellar metallicity, rotation rate, and jitter, and of course, and this is important, actual measurement schedule. And typically you do that by injecting signals and looking whether you can recover them. This is one example. This is for the radial velocity bias. This is another one. This is now quite old, but shows an initial estimate of the detection bias for the Kepler survey back in 2013. This year is now for direct imaging. So here, this is the contrast, the magnitude contrast that we can discover now as a function of the angular separation to the host star. And here, in this the direct imaging, we probe luminosity of these giant planets. And here we have the micro lensing. In principle, the axes are not exactly those. It's rather distance in units of the Einstein radius, and its mass, planet mass over stellar mass. We can convert that into such a map. And here we probe mostly clothed planets around M dwarfs. And accounting for this bias is important. Otherwise, the picture might get distorted. For example, the observed mass distance diagram, there are always a lot of hot Jupiters, but we know that they are actually rare if we correct for the bias. And what this plot here means, these two, which rely on planet radius and here on the magnitude of an object, this means that in the best case, the theoretical model should not only predict the masses and the orbits, but also the radii and the magnitudes directly, because it's actually not so trivial to get from mass to radius or luminosity, especially at the younger ages. And what is good about all these different techniques is that each probes a different aspect of the theory, and this helps to beat the parameter dependency of the global models, which is a weakness of this approach. Because these models, they combine so many submodels, and each submodel typically comes with one parameter or two or three. You end up in the lot with a lot of parameters. But if you can probe very different parts with a lot of observations, then you can try to beat that. And once we then have this detectable subpopulation, we then can compare this actual observation and see whether the model agrees or disagrees with these observations. And what you can take from that is that the large surveys with a well-defined bias, like of course space missions, but also big missions from the ground, they are best suited for comparisons in a population synthesis approach. And with that, we are done with the first part.